So what I want to talk about are how we're going to be able to learn or find compressed representation of functions, typically in high dimensions, using tensor networks. So I will do linear algebra, but go beyond matrices and to tensor objects. And I will do some kind of machine learning, but with linear algebra techniques. So that's the idea. So let me start by few introduction, by small introduction with tensors. Is there a pointer? Where is it? Oh, yeah, thank you. Tensors, basically what I mean by that here as n-dimensional arrays, with n indices that will run discrete values, typically from 1 to d. They are, generalization of matrices. There is no notion of symmetry. Sometimes there is some confusion due to different areas in physics and mathematics. Here's just a matrix in higher dimension. I will use a lot the pictorial representation of these objects, meaning we're going to represent the indices like legs, sometimes with the index themselves, sometimes without. And the contraction between two tensors will be depicted by connecting lines. So this is just a matrix, two indices. This is an n-dimensional tensor T with n indices. Sorry. The question I'm going to ask today is, how am I going to find low-rank decomposition of such tensors? So just a reminder, there is a lot of low-rank, very useful decomposition for matrices. SVD, singular value decomposition, QR, rank revealing QR, rank revealing LU. For example, if I decompose a matrix like an SVD, I will decompose it in this form with a diagonal matrix and two matrix U and V. Then if I want to approximate my matrix at some precision epsilon, I will typically keep the largest singular eigenvalue, chi, of them. Chi is the epsilon rank. I will that and refer it later as the rank or the bond dimension, because we use both in the quantum physics. So what it means is that I can cut basically my matrix and write it in the product of two smaller objects, U and D times V, where that's just an illustration of the pictorial rule I mentioned before. This index here, K, is contracted between these two tensors, and the external indices are I and J, corresponding to this formula, and K runs from 1 to chi. If chi is small, this is clearly much smaller object to store, because these two objects are much smaller than this one. So we're going to save memory and computing time. Think about a rank 1 matrix. You want to store it as two vectors, not as a large object, and you want to operate on it in this way. So my question today is, how are we going to generalize that to higher dimension? Turns out there are many ways to do that, and I'm going to focus on the simplest way, which is called the matrix product states or tensor trains. Both words are equivalent, coming from different communities. So the tensor will be written as a product of smaller tensors, which I represent here in this way, each of them carrying one external index. And the tensors are contracted with each other along this line with a bond or an internal index of dimension chi. So if you count the number of elements you have to define the tensor, the general one will require you d to the n elements. Here, however, if we look at this one, for example, we have d elements for the index and chi element for both indices here, which means chi squared d, and we have n of them. So we have this number of elements, which is clearly much smaller than d to the n if n is large and d is large. And again, we want to do this kind of calculations with some precision controlled by chi. And there are many other forms of interest, lattices, trees, but I will only focus on the simplest one, the train, just a line of tensor. And what we want to do, a tensor is fundamentally a function of its indices, right? And in reverse, I can consider, if I want, any function as a kind of tensor as a function of indices. So let me consider the function of n variable. Here is 8, for example. And imagine the argument is either a discrete index, or if it is not, I'm going to discretize on a grid or using a kind of polynomial in each dimensions. That doesn't really matter. I will not focus on this point here. Let's imagine that x has been discretized. What I want to do is to do this factorization in order to have a compressed representation of my function. Again, an approximation which I can control, and a form on which I can directly operate. And many operations will be easy to do directly in this form, therefore much more efficient than doing it in the original form. And all of that will be done with the linear algebra toolbox. This is different from compressing function in n dimension, let's say with neural network, which use nonlinear representations, are usually more expressive, require fewer parameters, but are usually less easy to manipulate to do various operations. So let me give an example what I mean by many operations. Just integration. Imagine I want to integrate that function in large dimension. We often have to do that. I mean, in quantum physics, we have to do that everywhere. We have to compute large dimension sums or integrals. That's a discrete version of this. And clearly, a priori, this is a difficult problem, right? That's why, in statistical mechanics, you have to compute partition functions and things like that. That's difficult because you have the curse of dimensionality. In order to compute this sum, a priori, I need d to the n operation. But if I can compress f as a tensor train, which means that f is written in this way, meaning it's a product of matrices, m1 of x1, mn of xn, so where each matrix is, let's say, is of dimension chi by chi, except at the boundaries, so that you have a scalar at the end. It's very easy to integrate because the variables are basically separated up to chi, right? So I can do the integration in one dimension for each of the matrices and then multiply them. So it's easy to do. The remarkable thing is that this very simple idea actually works. It works in some non-trivial problem, and I'll show an example a bit later. So the key question here is, if I give you a function, or any function you can compute, you have algorithms to compute, then can it be compressed in a tensor network? Not every function can do that. Similar question is, in which variable can you compress it? You may have a change of variable that does it or doesn't. That's a separate question. And if it does, how am I going to compute the decomposition? If possible, with a minimum number of calls to the function, because the function I'm working with usually are very expensive to compute, so I don't want to call the function too many times. And I want to do that with an error estimate and a control. I want to be able to refine my approximation. I want optimally to be able to go to machine precision. Right, so now the second part of the talk will be about presenting one tool. That's a tensor cross interpolation algorithm. It's a generic tool that will be able to do that. There may be cases where you have more optimal algorithm, but that's the simplest, well, one of the simplest algorithms to do that, I think. So I added here a couple of references. These really started with work in the mathematical community by Oseledets and Savostianov and collaborators in around 2010. We started to use it in quantum physics really in this paper 2 years ago, and since then there's been a lot of interest and activities in using that, at least in our field. We recently put a paper with many collaborators containing better understanding, in my view, of the algorithms and also libraries that you can use in order to try it yourself. I'll put the reference on the website at the end. This algorithm falls in the category of active learning algorithm, meaning what the algorithm is going to take is going to evaluate the function at some points, which basically are the n-dimensional generalization of Gauss pivots. And it's going to regularly find new points to evaluate the functions. Therefore, it's going to dynamically choose the points where to evaluate the function in various subplanes of the n-dimensional space. So to be contrasted with an algorithm that would take just a set of data where you have evaluated the function and just construct the tensor. You can also work in this way, but that's not what I'm talking about today. All right. So the basic summary of the algorithm is to say, I want to do this operation, and the algorithm will be able to do that with the following characteristics. First, it's going to do that with n operations, which is n d chi square, which is basically the number of elements which we need to compute. So it's going to be difficult to do less than that, because that's the number of points we need. Again, that's much less than computing the whole tensor. The algorithm is a rank-revealing algorithm, meaning you're going to run it, and you are going to have an error, epsilon of chi, that decreases when the rank chi is increasing, so you can control, with the caveat that you're, of course, in large dimension. Therefore, you know, there is always possibilities to have trouble. We can discuss that if there are questions. But in general, it works in this way. And also, very importantly, it fails when the function doesn't have the proper form. The error will simply not decrease, and the algorithm will tell you, you know, that it doesn't work. This is very useful properties because in most of the functions we are going to, for which we are going to apply these algorithms, we don't know a priori that the function has any form or you know, tensor form or tree form. We need to be able just to try it, see whether the algorithm reveals the factorization or not. So it's a yes or no answer, and it's easy to do. All right, so now to do that, there are going to be a couple of 4 or 5 slides which are slightly more technical. If you get lost a bit in the tensor indices, don't worry. Then after that, there are examples. But you know, tensors are slightly more complicated to handle than matrices. The tool I'm going to need is a tool of the decomposition of a matrix, a cross-interpolation, CI, hence the name of the algorithm, for a matrix. That's one of these low-rank decomposition for a matrix. So let's look at this. Imagine we have a matrix A, depending on U1 and U2, with discrete indices. I write it as a function here, just because that's a notation I will use later. We can find, if the function is of low rank, a subset of rows and columns indices. So subset of rows, I1, I chi, and columns, J1, J chi, chi of them, such that the matrix is approximated by this form here. Okay? So there are 2 components to this approximation. The red one is a slice of the matrix. You're taking here basically a couple of columns, chi columns of the matrix, and here chi rows of the matrix. So it's basically a slice which is slightly fat because in the other dimension of dimension chi. And in between here, so this matrix is of dimension d by chi. Here you have a submatrix of A, which is the evaluation on the pivots. That matrix is of size chi by chi, which you need to invert here. And this approximation here is an approximation of your matrix. Of course, here we are in the case where chi is much smaller than the dimension. That's what we should keep in mind. This representation has several properties. First, if the matrix is of rank chi, it's exact. And it's an interpolation. If I put here any pivots, for example, I2 here, this will cancel with this term and will give me exactly the slices. So hence the name, it's an interpolation of the full matrix given some rows and some columns. The question, of course, is how do you find those pivots? And there are several ways to do it. The way we now do it is using an LU decomposition because, in fact, this representation is equivalent to an LU decomposition. Full pivoting chi times. So in terms of graphical representation, I have a matrix here, and I decompose it again as the red part, the slice, the inverse pivots, and then the red part again. The same kind of diagrams. And the way to think about tensors can be you know, presented in this way, which is mathematically correct, but totally inefficient from a computational point of view. I'll correct that in a second. If you have a tensor of U1, UN here, you are going to slice this into 2. You are going to group all of the indices U2 to U5 into 1, cut here, and consider that as a matrix from the left part and the right part, and apply the CI, which we just had for a matrix. So you have a 1-dimensional slice here, a pivot matrix, and the rest, which turns out to be a smaller tensor with only 4 indices. This tells us immediately that the pivots, OK, here we are going to have one of the pivots, which I call U bar in this case. And here we're going to have pivots on this matrix, which are going to be multiplets. And that's the price you have to pay to work with tensors. You are going to have exactly the same idea, chi pivots, but they're all multiplets. And of course, then you continue to do the thing, if the computer wants to do it, yes? Some reason. OK, it doesn't work on this. OK, anyway. So you continue to decompose this one and then this one, and you arrive to this form. So you can write your tensor as a product of the slices times the inverse of the matrices, and you can, of course, regroup if you want the blue part into the red, and you have an MPS. Okay? Now, just to spend a little more time just writing things slightly more precisely, these T tensor are one-dimensional slices of the arrays. So you just let one of the index run and put the other ones on pivots, like this formula says. And that's just writing what I just said. The set of pivots are the chi pivots in both on the left and on the right, and each of them is a multiplet. And the size of the multiplet depends on your position on the tensors. They are alpha minus 1, size of alpha minus 1 on the left, size of n minus alpha on the right. But apart from this small change, it's just the CI decomposition or an LU decomposition. That's saying the same thing again. Here, that's full representations with pivots, at different positions. That's the tensor I just mentioned. The inverse is just the evaluation of the tensor on the pivots again. And this property, this form has a very nice property. It is again exact if you compute it on the one-dimensional slice, this approximation, exactly like the matrix was before, hence the name. It's just a tensor generalization of the CI. Now, the last things which you need to do, this is great. This tells you what the form is. It doesn't tell you at all how to compute it. Because if you try to compute it in the naive way, it's not going to work. And just very briefly, and again, if people are interested, we can discuss at length the algorithm. The idea is the following. On two-dimensional slices, when you free two indices of the tensor, the form is not exact, okay, by construction. So we're going to choose pivots to minimize the error in these two-dimensional planes. What we do is we take the tensors as a function of U1 and U alpha and U alpha plus 1. Again, cut it in two, make a matrix with the pivot indices here and there, and do a CI or an LU decomposition of it. So you do a piece of the decomposition, and that will produce to you the new pivots which you need. And the algorithm will sweep around the tensors back and forth and do this operation multiple times in all two-dimensional planes successively. That's how it's going to do the decompositions. The error that you're going to get in these decompositions, that's the error estimate we were looking for. That's the error that your calculation will yield at the end as a function of chi. And the larger you take your rank, the smaller the error is going to be. The remarkable thing, I think, well, it always surprises me, is that, sorry, this is not working very well. I can't, yes. You're doing this decomposition plane by plane in this way, then this plane, then this plane, then this plane, and so on, back and forth, right? And the remarkable thing is that it will converge after a couple of sweeps and give you the pivots. And if you want to have all the details, I mean, we can talk or we can have a look at the papers. So it's just a higher dimension generalization of LU or ghost pivoting. That's just what there is. The difficulty here is that to handle all the indices, and it's a bit scary because you have many legs, but it actually works. Sure.
Are you going to say something about how that, for instance, the very first step is done? You've got like you've got n indices on the U1, but you've got n to the d minus 1. You've got like this enormous
no, I don't.
matrix on
I don't,
on the
because
other
here
side.
I'm going to do the pi with the pivots. At the beginning, I basically have no pivots, so I'm going to have a very small matrix to do.
Okay, I'm kind of okay with this step, but like the very first step was like...
No, but the first step was just a way to show the form, mathematically, that the form will be this way. It's not a practical algorithm.
Oh, I see.
Right.
So you only have a...
It's just a naive way just to do it, but for the reason you mentioned, it's not a practical algorithm. It will be way too big. Okay. So the sweeping algorithm is the way to do it in practice. And then there are different forms of the algorithm, some that increase the ranks one by one. That's a traditional algorithm. Some of these that recompute all the pivots each time. That's the one we introduced recently, and for us seems to be more stable, but that's entering more technical discussions. More questions? Oh, yes.
Yeah, just a quick question. Is there any understanding of the uniqueness of the of the pivot matrix you get
No,
at
there
the
is
end?
no uniqueness.
Okay.
Because you can always choose different columns in different ways, but the result is the same.
With the gauge fixing there?
Yeah, it's a kind of gauge fixing.
Okay.
Now, let me take, I don't know, why does it want to go to the next? Yeah, okay. Two examples. Simple, I don't know. The first one is the one we started to use the problem for. So that's a quantum many-body problem. You don't need to know basically much about quantum physics here. We're solving problems of many quantum particle in interaction. Well, that's what we do at CCQ. And one of the techniques among many that we use consists in computing the perturbative expansion in the interactions. The interaction is weak, it's okay, it's getting bigger, you have more and more terms. And to do that, the core of the question is to compute large dimensional, extremely oscillating integrals. So the quantity of interest here is some quantity at order n, which is an integral of a function here, which we know very well. It's a sum of all Feynman diagrams for people who know a bit of quantum physics. That cost us an exponential time to compute, but we can compute it. We have ways to compute that relatively efficiently, and we can compute it, let's say, to order 20 or 30. My problem here is I have an integral to compute in dimension 20 or 30 or more. That's the simplest case, which can be very oscillating. And that's an illustration of one of the functions that comes into building this function. This function will be made of this function. You pick a determinant, and all of these take an exponential number of them. It will oscillate a lot. And more importantly, it will oscillate on a scale. Let's say it oscillates on scale, time scale, let's say 1. The physics I'm interested in will be on a scale 10 to the 2 to 10 to the 4. So that's not easy. Still, we can do it. Because the TCI is capable of decomposing this function along the line I mentioned before. You discretize, of course, the time in some grade, and you do the decomposition. Here is an example of a random slice of the function in n dimension, where the exact function is the orange curve, and the blue dots are the MPS with only 30 rank, which is very small for a tensor network. It doesn't cost much. As you can see, the function looks not very nice, but the fit is excellent. If you look at the error I was mentioning before that we get during the training process, forget the fact there are two curves, there are two estimators. Let's focus on one only. That's the error epsilon as a function of chi. In log-log plot, it decreases 1 over chi to the 4, so quite quickly. We don't know a priori why. I mean, I don't know if for which class of function it works. Just for my function, it just works at that very rate. That's what matters to me when I do that. There is no general theorem that tells me what the scaling and all of this. At least I don't know them. And it turns out that in this case, for some physical parameters, we know a completely independent mathematical solutions, which we can compute at machine precision. And therefore, we can compute the relative error of our numerical calculation to the exact mathematical calculations as a function of the number of points where we evaluate the integral. Again, that goes to 0 at a rate which is 1 over n to the square, 1 over chi to the square in the same way. And we can basically go to machine precision if we really want. This is to be compared with Monte Carlo that you would like to do in large dimension. That would go like 1 over square root of n with Monte Carlo. And of course, Monte Carlo would be in great trouble in the oscillating case. So these techniques looks simple and naive. You just decompose and integrate. But in fact, it works. And I would say that for many n-dimensional integration nowadays, I would say this is a first choice technique to try. And Monte Carlo being a default solution when the function cannot be factorized because it's faster, it gets to higher precision, and it has no sign problem. The main problem we have with quantum systems, of course, in Monte Carlo is the sign problem. We sum a lot of terms, positive and negative, and we have an exponential loss of precision. The reason is that factorizing a function has nothing to do with the sign of the function. The function can be extremely oscillating and still factorize. These are different things. Again, on the same problem, I can just tune some physical parameter that's going to make my function more and more oscillating in some sense. Here is the average sign of my integral, right? The integral divided by this integral. There's a piece here that's missing. That's the absolute value. We see that changing this parameter, I go to a sign of 10 to minus 5, which is dramatic for Monte Carlo. the error factorization for a fixed bond dimension using the same parameter doesn't change. Okay? So I can access regime which I could not access before. And the reason is that we are dealing with quantum systems here, and so in real time, what quantum systems like to do is to oscillate a lot, and they oscillate a lot. However, and that's something we discovered more recently, of course you are still in large dimension, so you will still have some of the problem that Monte Carlo has. And one of them is ergodicity. In some cases, the algorithm will not be able to find your function. If your function is there at some peaks in some very rare space in n dimension, it will become difficult. But we can design strategies which come from Monte Carlo to avoid this problem in some cases. And that's a more advanced point. I'll be happy to discuss and show examples if people are interested. In the last 5 minutes, I want to show another completely different example, which is a bit less linked to quantum physics. Until now, I was looking at functions of n variables. Okay, now I want to consider a function of one variable, maybe two. Okay, completely different animal. And I claim that a function of one continuous variables can also be viewed as a tensor with a little trick the following way. Take a function g of x between 0 and 1. Okay? I'm going to write x as its binary decimal decompositions in any base. Typically, we use base 2, but you can use base 10, so 0.2, 3, 5, whatever. Clearly, the function is a function of these. So I can view it as a tensor network where these are the indices. Okay? That's certainly true. The remarkable thing is that for many functions, this tensor is actually low rank, which is not obvious, but true. For example, if you think about exponential, you can, by direct inspection, look that, in fact, it has rank 1. And you can represent any exponential, any oscillating, crazy oscillating exponentials in this representation with a very low rank. Also, many functions, I will show a couple of them in a second, can be used in this representation. Also, the function can be directly manipulated in these representations, convolve, integrated again, do what people call ultra-fast Fourier transform. And this has many proposed applications. It's a lot, it has raised a lot of interest recently. TCR is a tool that will help you finding the representation of such a function. You can take the function and find the tensor representation. For example, a cosine, that's the sum of two exponential, rank 2. 20 cosines, rank 18. A cosine plus some cusps, no problem, rank 9. Just showing a few functions. Also, a quite bizarre function. My collaborator just chose this function, which is oscillating quite a lot. It's bad, looking bad. 12. With a rank 12, I can think, and the algorithm will learn it relatively quickly. You can find that in the papers. This is not limited to one dimension. I can do it in 2 dimensions. Here is a function in 2 dimensions which is designed to have extremely different time scales. There is huge numbers here and huge numbers here. It oscillates on extremely, quick, extremely fast. I can represent it with rank 50. Okay. These are the representation of the function with rank 1, 5, 20, 30, 50. It converges with chi increasing to the function. And this is the function if you start to zoom it. Zoom, zoom again, zoom again, zoom again at different scales. And in fact, we can reproduce all the different scales of the functions. And that's, again, learned by TCI. You put this in the TCI algorithm, you get that, and with an error. That's quite amusing. And to finish, more troubling even is that TCI seems to be able to find the global and maxima and minima. That's a recent proposal by these people, is that the pivot of TCI usually are closed or contains the global minima and maxima of the functions for reasons which are not totally obvious to me, but we can understand why. This is a calculation done by Miles here at CCQ on a 2-dimensional function and give you where the pivots are going to be located in these 2 places where it's going to be the max and mean. So there are a lot of interesting directions. If you want to play with it, there is open source code linked to our papers called tensorforall.org with my collaborators. Also, you can find some of it in iTensor. So you have the choice between different languages, Python, C++, Julia, everything. So you can have an implementation. And the conclusion is there is a lot of interesting things to do with this parsimonious representation function with tensor network. And TCI is a generic algorithms. It's just ghost pivoting in higher dimension, nothing more, but that's it. That will find many of these compressed forms. There are many current efforts to go beyond MPS, trees, in particular CCQ. And this is just a form of machine learning without any gradient descent, just with linear algebra. And on this, I will thank you for your attention. I'm out of time.
Can you highlight how TCI is different than this work by Alex Gorodeski on the function train decomposition?
There may be relations, but it depends for which kind of functions, right?
Right, I
if
mean
it's
that-
for
that- so
low
that-
dimension functions you're talking about?
Right.
Yes, there may be relations. You know, I can't answer for sure, but we should discuss.
Okay.
I know you, yes.
So could you go forward to the 2D, yeah, the back one. So the one slide back where you have this.
I'm sorry. Yeah.
Yeah. So I'm wondering about the like smooth. Well, I mean, of course, this is a very very rough function, but like it's smooth.
It's smooth. Yes.
And but when you look at chi = 5, that representation does not look smooth. And say I wanted to compute the derivative of such a function, is there a way of still doing that in a nice way with a low representation?
With a small chi?
Yeah, yeah.
I don't think so, because you would need to, there is also another parameters to play with here, is the number of bits you actually take of your functions, right? So this has been pushed to a large dimensions. I would be careful in using that for a derivative, but to be tried. I mean, I have nothing very deep to say about it. Yeah, there's a question on the back.
Did I understand correctly that there are no error bounds for this method?
Well, there is an error estimate which we compute on the fly.
Right.
But error bounds would mean that, you mean a priori?
Yes.
No, I don't know. Because,
Because-
there are clearly classes of function that will be compressible. But I don't know how to prove. I mean, okay, in the general n-dimension case, right? For the quantics, there are theorems, and Miles knows them better than I do. But I don't think that they are, practical bounds. I think that's fair to say.
Right. Because I feel like if slices of your functions are sort of analytically, you can extend it into the complex plane analytically, then you should have some error bounds, because that's at least true for the bivariate case.
It's maybe true. I don't know for the function we are really using in many-body problems, because they're so complicated that I don't know how to do that, but it's a very interesting question to ask. It would be great to know a priori. It would be great to know. I just don't know. Alex, you had a question.
So the ordering of your indices is clearly very important.
Critical.
Do you have some way to, in the optimization, to sort of juggle that around, or have you thought about ways to reconnect, maybe break the train, and move it around in some kind of genetic algorithm or something that tries different topologies there?
It's an excellent question.
If you don't know how to order things,
Yes.
you don't.
It's an excellent question. The short answer is no.
Okay.
I mean, the idea on papers, but nothing I've been playing with. Maybe you had some ideas. Do you want something?
Some work about dynamically reordering them in the setting where, not with TCI exactly, but in the setting where people are just using them for like high-dimensional quantum state wave functions, and there's been some successful work there.
But now, for the first part of the talk, it comes to the question of choosing the right variables. So I cheated a little bit because time. You learn not the function of time, but the function of time differences between ordered times. And if you don't, it doesn't work. And that, which is similar to your question, how you organize the variables, that's a human input at the moment. We don't know how to do that. Maybe there are ways to optimize on that. It would be great. There are physical reasons we understand why to do that, but in general, I don't know. I don't think there is a general solution.
In your work,
Didn't start because you looked at asymptotics, right? You thought, what if all the variables are
Yeah,
far
yeah,
apart?
for two reasons.
Yeah.
You're correct, thanks. For the reason is that in our work, we can look at the function at large distance, large time difference, and then we can find analytically the form and find the MPS. So we knew at long distance it was correct, and then the surprise somehow that it works to any distance. Also, there is a physical reason. If you do in n dimensions, the TCI, the first version of it, when you have n variables, doesn't like discontinuities. Or these functions are full of heaviside function and discontinuities. So the change of variable we did was to put all of discontinuities at the border of our hypercube. Then that would be a solution. That was the physical motivations. These are details, but important details. And if you don't, but the point is, if you don't, the algorithm will tell you that you failed. It doesn't take a long time. It just fails quickly. It's like the SVD. It's just